Hello, my dear students. Welcome to my YouTube channel, That's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp3 hybridization, and for this hybridization, I'm taking the example of methane molecule. So let's talk about the methane today. That's methane, and it's CH4 molecule. Before doing the hybridization, let's make the Lewis structure of the CH4. So that's a carbon over here, hydrogen, 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 and the hydrogen. Let's talk about the carbon. What's the atomic number of carbon? It's 6. So the configuration will be 2, 4. That means carbon is having 4 electrons in its valence shell. So let's mark these 4 electrons around the carbon. The first electron, second electron, third electron, and the fourth electron. And let's talk about the hydrogen. The atomic number of hydrogen is 1 and its configuration is 1. That means hydrogen is having only 1 electrons in its valence shell. So let's mark it. Now first hydrogen having 1 electron, second hydrogen 1 electron, third hydrogen 1 electron, and the fourth hydrogen 1 electron. Now all these hydrogen will make 1 covalent bond with the carbon. Now we'll all know that hydrogen will have duplet in its valence shell because the nearest stable noble gas configuration for hydrogen is helium, which is having 2 electrons in its valence shell. So here let's count the number of valence electron of hydrogen after the formation of one bond with the carbon. That's first electron for first hydrogen and the second electron for the first hydrogen. So the hydrogen attained the duplet. Now let's talk about the second hydrogen, the 1 and the 2. Second hydrogen also attained the duplet. Now let's count the electrons for the third hydrogen. The first electron, second electron. The third hydrogen also attained the duplet. And let's talk about the fourth hydrogen. I'm counting the electrons, the first electron and the second electron. So fourth hydrogen also attained the duplet in its valence shell. Now let's talk about the carbon. I'm going to count the number of valence electron of carbon after the formation of 4 bonds with the 4 hydrogens. So that's number 1, number 2, the third electron, fourth electron, fifth electron, sixth electron, seventh electron, and the eighth electron. So the carbon also attained the 8 electrons, that is octet in its valence shell after the formation of 4 bonds with the 4 hydrogens. Now here in total we are having total of 4 covalent bonds, and all are the sigma bonds, that is 4 sigma bonds. Now let's talk about the hybridization of carbon in CH4, because in CH4 the central atom is carbon. Here central atom is carbon because carbon is forming maximum number of bonds in CH4, that's 4 bonds. Now carbon, what's the atomic number? 6. What's the valence electronic configuration in terms of orbitals? That's 2s2, 2p2. So let's make the orbital diagram of the carbon in the form of boxes. That's 2s. In 2p we are having 3 degenerate orbitals, that is orbitals with equal energies. Now the 2s is having 2 electrons, so that's the first electron with a spin of plus 1 by 2, and that's the second electron with a spin of minus 1 by 2. Now 2p is also having 2 electrons, so we have to follow the Hund's rule, first electron and the second electron. Now, let's come to the Lewis structure. In Lewis structure, carbon is forming 4 bonds. That means in the electronic configuration of carbon, we need to have 4 electrons in different atomic orbitals, so that 4 atomic orbitals containing one electron each can overlap with the orbitals of hydrogen to form the 4 sigma bonds. So that means we need to have 4 electrons in different 4 atomic orbitals, and for that we need to jump or excite one electron from 2s to the 2p orbital of the carbon. First of all, this was the ground state. When the electron is excited to the higher energy level, then that's called excited state. So let's make the excited state now. That's 2s, and that's our 2p. Now all the orbitals are having one electron each, and now carbon is eligible to form 4 covalent bonds with the 4 hydrogen atoms, because I have already told you in the previous lecture also, when the 2 atomic orbitals of different elements overlaps with each other, then both of the orbitals must have 1 electron each for the formation of the covalent bond. Here in Lewis structure, the carbon was forming 4 bonds. That's why we need 4 atomic orbitals of carbon that must have one electron each, that can overlap with the s orbitals of the 4 hydrogen to form the 4 sigma bonds with the 4 hydrogen atoms. So that's why we have excited an electron from 2s to the 2p. So that's our excited state. That's the excited state of the carbon. Now, from here, hybridization will take place. From here, hybridization will take place. The one of the s orbital and 3 of the p orbitals will intermix with each other. One s orbital and 3 p orbitals. They will intermix with each other. And that intermixing of atomic orbitals is called hybridization process. That's hybridization process. So here total 4 atomic orbitals are mixing, the 1s and the 3p. So after intermixing, we are going to have 4 new hybrid orbitals. 4 new hybrid orbitals, and they are also degenerate. That means all the hybrid orbitals will have equal energies. Here 1s and 3p, total 4 atomic orbitals are mixing. That's why we are getting 4 new hybrid orbitals. So these are 1, 2, 3, 4. We got the 4 new hybrid orbitals. So what's the name of these hybrid orbitals? As 1s and 3p are mixing, that's what will be called as sp3 hybrid orbitals. So in sp3 hybrid orbital, there will be 25% s character and 75% p character per hybrid orbital. So I have written the first orbital to be sp3, second orbital will also be sp3, the third one will be also sp3, and finally the fourth one will also be the sp3. So we got the 4 new hybrid orbitals, that's 4 sp3 hybrid orbitals. Now let's come back to the configuration. How many electrons we were having? The 1 in the 2s and the 3 in the 2p. So we were having 4 electrons in total. So there will be the redistribution of that 4 electrons in all the 4 sp3 hybrid orbitals according to the Hund's rule. So the first electron, second electron, third electron, and the fourth electron. So here the hybridization process is completed. Now let's talk about the hydrogen. Now I am talking about hydrogen. What's the atomic number of hydrogen? It's 1. So its configuration will be 1s1. So that means in s subshell we have only one orbital. So that's 1s of hydrogen, which is having one electron. So this 1s of hydrogen will have an head-on overlap with the sp3 hybrid orbital of the carbon to form the sigma bond. So that's the sigma bond sp3s, because it has been found by head-on overlap of sp3 hybrid orbital of carbon with the s orbital of the hydrogen. Now let's talk about the second hydrogen. That's again hydrogen, 1s1. That means it's having one electron, and this 1s orbital of hydrogen will have an head-on overlap with the sp3 hybrid orbital of the carbon. So it's again the sigma bond that have been formed by head-on overlap of sp3 with the s orbital of the hydrogen. So it's sigma sp3s. Now let's talk about the third hydrogen. I'm talking about the third hydrogen. That's again 1s1 as the third hydrogen, as having one electron. Now again this 1s of hydrogen will have an head-on overlap with the sp3 hybrid orbital of the carbon. So it's a sigma bond. So it's a sigma bond that has been formed by the head-on overlap of sp3 hybrid orbital of carbon with the s orbital of the hydrogen. Now let's talk about the fourth hydrogen. It's again 1s1, and that's our fourth hydrogen, and it's having one electron. Now this again 1s will have an head-on overlap with the sp3 hybrid orbital of carbon to form the sigma bond. So it's again sigma sp3s. Why? So it's an head-on overlap of sp3 hybrid orbital of carbon with the s orbital of the hydrogen. So that's all about the hybridization of carbon in case of CH4. Now let's make the structure. Here carbon is showing sp3 hybridization. In case of sp3 we are having tetrahedral structure. We are having tetrahedral structure. You have to understand this structure in 3 dimensions. That's central carbon over here. So that's the first hydrogen. That's the second hydrogen. Now these two bonds are on screen. Please try to understand. These two bonds are on screen. Now this is called wedge. This is called wedge. Wedge stands for, that means this bond is coming out of the screen. Try to understand. This is called wedge. Wedge stands for this bond or this hydrogen is coming out of the screen. That's called wedge. And that's called dash bond. That's called dash bond. And hydrogen over here is going inside the screen, and the remaining two bonds are on the screen. Try to understand again. The wedge bond is coming out of the screen, dash bond is going inside the screen, and the another two bonds that have been shown by simple line is on the screen. So that's our CH4, and the structure is tetrahedral, and here the bond angle is 109 degrees and 28 minutes. All the angles are equal. That's also 109 degrees and 28 minutes. After that, this bond also, that's 109 degrees and 28 minutes. All the bonds are of 109 degrees and 28 minutes. After that, this bond also 109 degrees and 28 minutes, and even this bond also 109 degrees and 28 minutes. Try to understand this structure in 3 dimensions, only then you will be able to get that all the angles are equal and of the equal strength, because all the bonds are sigma bond that have been formed by head-on overlap of sp3 hybrid orbital of carbon and the s orbital of hydrogen. That's why I'm writing all the bonds are of equal strengths. Moreover, all bond angles are equal, that is 109 degrees and 28 minutes. But the point is, you have to imagine this structure in 3 dimensions, only then you will be able to understand it. So at last, let's talk about the energies. Here, first of all, here's the consumption of promotional energy, because there's an excitation of electron or the promotion of electron from 2s to 2p. So is the consumption of promotional energy. After that, during the intermixing, here's the consumption of hybridization energy. Here's the consumption of hybridization energy. After that, during the formation of 4 sigma bonds, I'm writing during the formation of 4 new sigma bonds, comma, there is release of energy. There is release of energy which recovers or compensates, promotional as well as hybridization energy, as both of the endothermic processes, promotional energy and the hybridization energy, is compensated during the formation of 4 new sigma bonds. That's why formation of CH4 is practically visible. So that's all about the CH4 and the sp3 hybridization. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.